Hey guys, excited to be here with you today. We're going to be studying the chemistry of unsaturated and saturated fats. I've always been interested in trans, saturated, and unsaturated fats and the difference between all of them because we encounter them in our diets every single day. So I thought it'd be unique to investigate how unsaturated bonds affect the reactants, products, product stability, and equilibrium potential based on the chemistry of their reactions. So today I will investigate two unsaturated oils, soy and sunflower oil, and I will investigate two saturated oils, coconut and palm oil. For these four oils, I will determine the energy density in megajoules per kilogram. I will determine the crop yield, the temperature ignition, and compare vapor pressures to see which one makes for the best fuels and which one could potentially make for the best foods. So first we're going to start with the standards of efficiency by which we can judge each and every one of these oils. So for gasoline, standard energy density is 45 megajoules per kilogram. And the oxygen in the reactant, since it's octane C8H20, the oxygen in reactants is 0%. And because of that, we'll see that the NOx formation is also 0%. As far as the yield of crops is concerned, because that is of particular importance for biodiesel, the crop yield for an average farm is 110 gallons of oil per acre, and the energy input on average is 8.75 gallons of fossil fuels per acre. So an energy return on investment of roughly 12.5. The first oil we'll be investigating is the unsaturated oil known as sunflower oil. Energy density is 37 megajoules per kilogram, and the yield is 102 gallons per acre. Now the fat breakdown on sunflower oil, as we can see over here, is mostly polyunsaturated, close to 70%, whereas monounsaturated is 20%, and the saturated fats are only 11%. So we can see over here in the diagram that the polyunsaturated fats, along with the esters that are already in the oil, make it a very oxygenated fuel. 11% if those double bonds do not react, whereas it's 18% if those double bonds do in fact react with oxygen and form even more ethers and esters in the middle of the oil. So when oil is in the reactant of a fuel, that leads to NOx formations, because in order for that oxygen to be released, nitrogen has to react with it and form NO2 or N2O, other NOx fuels. So that makes sunflower oil a really poor fuel because of the high oxygen content. It has a lot of minerals in it though, which makes it a really good food, and that cis formation is very valuable to reduce the concentration of harmful substances in one's body. So it's good for food. Soy oil is the next unsaturated fat that we're going to look at today. It's got an energy density of 38.37 megajoules per kilogram. The fat breakdown on soy oil is a little more saturated fat, 16%, monounsaturated, also a little higher, 24%, and the polyunsaturated is around 60%. So we can see that there's still a lot of unsaturated bonds going on, particularly in that molecule there, and a couple double bonds there. So when we're going to decide whether this soy oil is best as food or best as fuel, we need to consider how long it's going to be out in oxygen for, because again, if it's subject to oxygen, some of these double bonds can break and make even more oxygen content in your fuel. So naturally, the oxygen content in the soy oil is roughly 10%. But again, in a vacuum, in the presence of oxygen, some of these double bonds can break. And any oxygen in your fuel above 10% is going to lead to a lot of NOx formations that you really cannot have in a fuel. So again, the oxygen percentage can get up to as high as 25 if all of those aromatic bonds do in fact break. The yield is 48 gallons per acre, which is about half as much as the yield for other plants. It requires 5 times more land than ethanol production, so detriments there. Coconut oil, that is a saturated oil for the most part, as we can see. It's got a few unsaturated bonds, but the polyunsaturated is only 3%. Monounsaturated 6%, saturated is 91% of the bonds. So as we can see over here, the yield is very high. This is because when there are saturated bonds, molecules can get much more close together than they can in the cis formation of unsaturated bonds. So that allows them to pack much more closely, get a yield 5 times, 6 times higher than what we saw for the unsaturated oils. So that's a big deal in energy production. But unfortunately, coconut oil is unstable, and the temp of combustion is 500 degrees Celsius. So it really is not a very combustible fuel, and that hurts its fuel efficiency. As for food, it is, like I said, unstable, not subjective to oxidative attack, so the body doesn't really like it very much. It's a little too tart. Palm oil, last unsaturated oil we're going to look at today. Energy density 37, you'll notice that's the same as, right around the same as for the unsaturated oils. However, palm oil is by far the most dense in yield, 650 gallons per acre. Now that's because in one fruit of palm oil, you get 2 oils. So the density there doubles right away off the bat. And it's still highly unsaturated. So as we can see in this diagram, those aromatic bonds do not often get attacked by oxygen. So it's pretty unsaturated, and therefore it has normal temperature of combustion, makes it a decent fuel. However, the energy density is a little low because, again, it packs really closely together. Palm oil has more revenue per area than any other crop because, as we can see, it sells 52%, comprises 52% of all the oils sold internationally. So we can see that this is, in fact, the crop that most farmers in the oil industry do in fact go to. It's got the highest yield in density, and the energy density is not much far off behind mineral oil, which, as we saw earlier, is 44 megajoules per kilogram. So considering all the yield that we get and the decently high energy density and the stability of the fuel itself, palm oil is a decent fuel. But again, the aromaticity makes combustion very difficult. It's a semi-solid, and oxygen reactions make NOx formation to break off those oxygens that are already in the fuel before combustion even happens. So again, NOx formation is not the best thing that we're looking for. In conclusion, bio-oils, since they contingently have oxygen in them, they must make NOx. Therefore, I suggest that bio-oils are not the best suited fuel to replace gasoline, because as we see with gasoline, it's saturated bonds and there is not a whole lot of oxygen in there. So the NOx formation is limited and the energy density is optimized. So I think if traditional oils are to run out, we should not look towards bio-oil to replace it, because that would only make our environmental issues worse. I'd say our best bet now is to go with Tesla's start investing in electric cars, so then we can use the solar industry, which is growing rapidly, to power such vehicles from our homes and from local stations that we can establish on highways and whatnot. So I think that's the best course of research for the future. I hope you enjoyed this presentation on the chemistry of oils, and thank you very much for your time. Here are my sources. About 5. Do Clemente Why Biofuels Can't Replace Oil, the Alternative Fuels Data Center, Wikipedia, I looked for the energy content of vegetable oils, and an article on biodiesel. In BioGrace, we have the condensed list of standard heating values, and from Soyatech, I got a lot of my facts on palm oil and why they're so dense. Again, thank you for your time.